For years, people have turned to diet soda as the guilt-free answer to sugary beverages. No calories, no sugar, no problem. Or so it seems. The label might say, diet. But what does that actually mean for your metabolic health? When we dive into the biochemistry, the endocrinology, and the research behind what these beverages do to the human body, especially in relation to blood sugar and insulin, we find a very different story than what marketing has told us. And it begins with understanding how the body interprets sweet taste, regardless of calories. When you consume something sweet, whether it's sugar or a zero-calorie sweetener like aspartame, sucralose, or saccharin, your tongue registers sweetness through taste receptors. But these receptors do more than create taste. They send signals to the brain and the gut. The brain, particularly the hypothalamus, begins to prepare for glucose metabolism. The pancreas in some individuals may begin to increase insulin secretion in anticipation of incoming sugar, even if none arrives. This is known as the cephalic phase insulin response. What this means is that just sensation of sweetness, even without real sugar, can trigger hormonal responses that set the stage for changes in blood glucose regulation. Now, you might think, if there's no sugar in diet soda, how could it possibly raise blood sugar? The answer is complex. Studies show that artificial sweeteners may not directly spike blood glucose like regular sugar does. However, they can affect the way the body handles real sugar when it does come. One key mechanism is through alterations in the gut microbiome. The trillions of bacteria in the human gut are deeply involved in glucose metabolism, and artificial sweeteners have been shown in both animal and human models to shift the composition of this microbial community. When certain microbes become dominant, they may increase glucose intolerance. In fact, research published in journals like Nature has shown that mice consuming artificial sweeteners develop significantly higher glucose levels than those drinking water or even sugar. Furthermore, these changes in gut bacteria may affect incretin hormones such as GLP-1 and GP, which play a role in insulin release and satiety. Altering these hormones can affect how the body responds to meals, how full you feel, and how insulin is secreted in response to food. If artificial sweeteners disturb this intricate system, you could see impaired glucose control even if you're not consuming sugar directly. That's the paradox of diet soda. It may avoid the immediate sugar spike, but contribute to long-term insulin resistance. Let's look deeper at the epidemiological data. Several large-scale observational studies, including those from the Nurses' Health Study and the San Antonio Heart Study, have reported an association between diet soda consumption and an increased risk of type 2 diabetes. Even after adjusting for confounding variables like BMI, age, and physical activity, the link remained. Now, correlation doesn't equal causation. But when these findings are layered over mechanistic research showing changes in gut microbiota, insulin signaling, and glucose tolerance, a plausible story emerges. Artificial sweeteners may create a metabolic environment that's more prone to dysregulation. Now, consider the behavioral psychology angle. Diet soda is often used as a license to indulge elsewhere. There's something called caloric compensation. Someone might think, I had a diet soda, so I can have the fries. This subconscious justification can lead to an overall increase in caloric intake, negating any benefit from choosing a zero-calorie beverage. Additionally, frequent exposure to intensely sweet tastes, much sweeter than natural sugar, can recalibrate the brain's reward pathways. This can make natural foods like fruits and vegetables seem less satisfying and reinforce cravings for ultra-processed sweet foods, potentially worsening dietary habits and leading to spikes in blood glucose through indirect means. Let's not overlook the potential impact on pancreatic beta cells. There's emerging animal data suggesting that artificial sweeteners might impair beta cell function over time, reducing the capacity of the pancreas to produce insulin effectively. While human studies are still catching up, the early signals are enough to warrant caution. If beta cells become dysfunctional, even small disturbances in glucose levels can have exaggerated effects, setting the stage for prediabetes and type 2 diabetes. There's also evidence that artificial sweeteners can disrupt signaling in the hypothalamus, affecting hunger regulation. If appetite increases, people may eat more frequently or in larger quantities, leading to post-meal glucose surges. Moreover, the metabolic confusion caused by these sweeteners can potentially uncouple the association between sweetness and energy, confusing the body's innate ability to match energy intake with energy expenditure. Over time, this may promote weight gain, visceral adiposity, and insulin resistance, all of which are tightly linked to elevated blood sugar levels and increased risk of chronic metabolic disease. When someone drinks a regular soda, the sugar rush is expected. Glucose enters the bloodstream, insulin is released, and the body begins the process of using or storing that sugar. But what happens if someone drinks a beverage that contains no sugar at all? Something labeled diet or zero. The assumption is that there should be no insulin response because there's no sugar to manage. But the body doesn't operate purely on labels or nutritional facts panels. It operates on signals, neurochemical, hormonal, and sensory. And one of the most powerful signals is sweetness itself. Whether the source is sugar, sucralose, aspartame, or saccharin, the tongue detects sweetness, and that detection sets off a cascade of physiological responses well before any sugar or lack of it, enters the bloodstream. At the level of the tongue, there are specialized taste receptors that recognize sweet molecules. These receptors are not limited to detecting natural sugars like glucose or fructose. They also respond to artificial sweeteners, sometimes with even greater sensitivity due to the intense sweetness of synthetic compounds. But what's important is what happens downstream. As soon as sweet taste is registered, signals are sent to the brain, particularly to the hypothalamus and brainstem, areas that control hunger, metabolism, and energy balance. These areas begin to anticipate caloric intake. The body, expecting glucose, may preemptively trigger hormonal responses such as insulin secretion. This early phase insulin release, known as the cephalic phase insulin response, is a form of metabolic anticipation. It's the body preparing for sugar that may never arrive. This mechanism is both fascinating and potentially problematic. When artificial sweeteners repeatedly stimulate this early insulin release without delivering actual glucose, the body may become confused. Over time, this mismatch between sweet taste and caloric content could blunt the effectiveness of insulin signaling or desensitize the regulatory pathways that depend on reliable feedback loops between taste, ingestion, and nutrient absorption. Some researchers have proposed that this disconnect can promote insulin resistance in certain individuals, especially those with existing metabolic vulnerabilities. Staying from processed foods, phenomenon might help explain why, paradoxically, some people who consume diet sodas regularly still struggle with blood sugar issues, even though they're not consuming traditional sugar. What's also notable is that insulin is not just response to rising blood glucose, it's a central hormone with wide-reaching effects on appetite, fat storage, and inflammation. So, even in the absence of sugar, if diet soda consumption results in an insulin surge, it may still drive metabolic consequences. For example, insulin promotes the storage of nutrients, particularly in fat cells. If the hormone is elevated without corresponding caloric intake, the body may begin to operate inefficiently, storing energy it doesn't have, increasing hunger to balance the mismatch, and creating a cycle of cravings and compensatory eating behaviors that undermine metabolic stability. Additionally, this early phase insulin secretion has been documented in multiple studies. In certain trials, subjects given artificial sweeteners experienced measurable increases in insulin levels despite the absence of glucose. This effect isn't uniform across all individuals, which suggests a degree of variability. Potentially by genetics, baseline insulin sensitivity, microbiome composition, and even past exposure to sweeteners. But the mere fact that insulin secretion can be stimulated in response to non-caloric sweeteners underscores the importance of re-evaluating the assumption that diet sodas are metabolically inert. Another layer of complexity comes from the possibility that artificial sweeteners may interact with sweet taste receptors in the gut, not just the tongue. The gut is lined with enteroendocrine cells that contain sweet taste receptors, and when these are activated, they can trigger the release of hormones like GLP-1, glucagon, like peptide-1, which modulate insulin secretion, appetite, and gastric emptying. When artificial sweeteners reach these receptors, the body may again respond as if sugar has entered the system. If this occurs repeatedly without caloric follow-through, the signaling pathways may become dysregulated, potentially affecting both insulin response and satiety cues. It's also important to consider how the brain processes the experience of sweetness over time. Ingesting high-intensity sweeteners may condition the brain to expect a certain reward from sweet tastes. When that reward is repeatedly uncoupled from caloric satisfaction, it may drive compensatory eating. This can further complicate insulin dynamics because the net effect may be increased calorie consumption from other sources, leading to elevated post-meal blood sugar levels and secondary insulin responses that contribute to glycemic volatility. The human gut is an intricate ecosystem containing trillions of microorganisms, bacteria, fungi, viruses, and other microbes that play a central role in regulating everything from digestion to immunity to glucose metabolism. This complex internal environment is known as the gut microbiota, and its balance is critical for maintaining metabolic health. One of the most overlooked effects of artificial sweeteners in diet soda is their impact on this delicate microbiome. While marketed as harmless substitutes, these compounds do not simply pass through the body unnoticed. They interact with the gut lining and microbial environment in ways that can impair glucose tolerance over time. Research has shown that artificial sweeteners such as saccharin, sucralose, and aspartame are not inert. Once ingested, they can reach the colon where they encounter the microbial populations that reside there. These microbes have the ability to ferment and metabolize even compounds that are considered non-caloric for humans. Several landmark studies have demonstrated that when artificial sweeteners are introduced into the gut, the microbial composition can shift significantly. Certain bacterial species proliferate while others decline, leading to a state known as dysbiosis, microbial imbalance that can interfere with normal metabolic processes. This shift in microbial populations has far-reaching consequences. In controlled studies involving both animals and humans, consumption of artificial sweeteners has been associated with a reduced ability to process glucose. In one prominent study, mice fed saccharin developed glucose intolerance within just a few days. When researchers transplanted the microbiota from these mice into germ-free mice, mice that had no prior gut microbes. The recipients also developed glucose intolerance, even though they had never consumed the sweeteners themselves. This finding strongly suggested that the altered microbiome, not the sweetener alone, was responsible for the impaired glucose metabolism. The mechanism by which gut microbes influence glucose tolerance is multifaceted. One of the key pathways involves short-chain fatty acids (SEC phase), which are metabolic byproducts of microbial fermentation. SFs like butyrate, acetate, and propionate play a role in maintaining the integrity of the gut lining, reducing inflammation, and regulating glucose uptake in tissues such as the liver and muscle. A balanced gut microbiome produces FCFAs in a way that supports insulin sensitivity and blood sugar regulation. However, when artificial sweeteners alter the microbial composition, the production of these beneficial compounds may decrease, contributing to increased systemic inflammation and impaired insulin signaling. Moreover, the integrity of the gut barrier, often referred to as the gut lining, can be compromised by microbial imbalance. A weakened gut lining becomes more permeable, a condition known as leaky gut, allowing endotoxins like lipolysaccharides (LPS) to enter the bloodstream. These substances can trigger low-grade chronic inflammation, which is a recognized driver of insulin resistance. This inflammatory state, even in the absence of dietary sugar, may raise fasting insulin levels and reduce ability to regulate postprandial glucose effectively. What adds to the concern is that individuals respond differently to the same artificial sweeteners. In clinical trials, some people experience significant metabolic disruption after consuming diet soda, while others do not. The determining factor often appears to be the baseline composition of their gut microbiota. This personalized response suggests that artificial sweeteners may only trigger glucose intolerance in those who already have certain microbial vulnerabilities. However, it also highlights how unpredictable the effects of these substances can be, especially when consumed regularly over long periods. Another important consideration is the interaction between artificial sweeteners and bile acids, which are released during digestion to help break down fats. Gut microbes help metabolize these bile acids into secondary bile acids, which play a role in regulating glucose and lipid metabolism. Disruption of this process through microbial imbalance can further impair the body's ability to manage blood sugar levels. Additionally, certain microbial byproducts can interfere with signaling pathways involving GLP-1 and PY, hormones that influence insulin secretion and satiety. Disruption of these pathways may lead to increased appetite, reduced insulin sensitivity, and more erratic blood sugar levels. Emerging data also suggest that the gut-brain axis, the bidirectional communication network between the gut and the central nervous system, is affected by changes in microbiota caused by artificial sweeteners. Alterations in microbial populations may influence circuits involved in appetite, reward, and glucose regulation. This could further amplify the metabolic impact of diet soda by affecting eating behavior, food preferences, and hormonal responses to meals. When we look at the long-term implications of diet soda consumption, one of the most striking findings is its consistent association with an increased risk of type 2 diabetes. This correlation has emerged across numerous large-scale epidemiological studies involving diverse populations. At first glance, the idea seems counterintuitive. Diet sodas contain no sugar, no calories, and are often chosen specifically by those attempting to avoid blood sugar spikes. Yet, despite their sugar-free status, these beverages appear to be linked to higher rates of insulin resistance and metabolic disease over time. Understanding how this paradox exists requires a deep dive into the layers of evidence and mechanisms that support this association. Multiple cohort studies have tracked individuals over years and even decades to monitor their beverage choices and subsequent health outcomes. In the seheult study, one of the largest and most respected long-term observational studies, researchers found that women who consumed at least one diet soda per day had a significantly higher risk of developing type 2 diabetes compared to those who rarely or never consumed these beverages. Similar results were found in the San Antonio Heart Study, which followed participants for over 7 years. In this study, both men and women who regularly drank diet soda had more than double the risk of developing obesity and diabetes than non-consumers, even after controlling for baseline weight, age, and physical activities. One important distinction to make is that these findings do not imply direct causation. Observational studies can reveal associations, but they cannot prove that diet soda alone causes diabetes. However, when such consistent correlations are observed across multiple studies and are supported by plausible biological mechanisms, they provide strong grounds for concern. The hypothesis is that artificial sweeteners, although non-caloric, may set in motion a series of physiological changes that gradually undermine insulin sensitivity and disrupt normal glucose homeostasis. For example, one possible pathway involves the repeated stimulation of the sweet taste receptors, which can influence insulin secretion and appetite regulation. Over time, this may contribute to metabolic dysregulation even in the absence of sugar. Another possibility is that individuals who consume diet soda regularly may unconsciously make poor dietary choices elsewhere under the impression that they've saved calories. This compensation effect can result in a net increase in calorie intake and postprandial glucose excursions, promoting insulin resistance over time. There is also the potential contribution of altered gut microbiota, which, staying away from processed, has been shown in experimental models to reduce glucose tolerance and elevate blood sugar levels following artificial sweetener exposure. Even when researchers attempt to control for these behavioral and lifestyle factors, such as body mass index, diet quality, exercise levels, and smoking status, the association between diet soda and type 2 diabetes often remains. This residual association implies that something beyond lifestyle compensation is occurring. When combined mechanistic studies showing changes in insulin response, microbiome composition, appetite signaling, and metabolic hormones, the case against long-term diet soda consumption becomes more robust. In clinical trials where individuals were randomized to consume diet soda daily, changes in insulin sensitivity and glucose metabolism have been documented. Some of these studies show that switching from sugar-sweetened beverages to diet soda improves short-term glycemic control. But over the longer term, metabolic adaptation and compensatory eating behaviors may negate those benefits. Additionally, the intense sweetness of artificial sweeteners, often hundreds of times sweeter than sugar, can recalibrate the brain's perception of sweetness. This may lead to increased cravings for sweet foods and decreased satisfaction from naturally sweet items like fruit, ultimately pushing individuals toward more processed carbohydrate-rich foods that elevate blood sugar. Importantly, the burden of diabetes is not simply about elevated glucose levels. It is about the cumulative effects of metabolic dysfunction over time, how the pancreas, liver, muscles, and fat tissue respond to insulin, how inflammation spreads systemically, how appetite and satiety are regulated, and how consistently the body maintains energy balance. The evidence suggests that regular consumption of diet soda, despite its zero-calorie label, may contribute to these subtle yet progressive disruptions in metabolic signaling. Over time, these disruptions may manifest as impaired fasting glucose, elevated hemoglobin A1C, and eventually, clinical diabetes. The experience of taste is more than just a matter of flavor. It is a direct communication with the brain's reward and regulatory systems. When someone consumes a diet soda, the sweetness they perceive is not just a sensory delight, it is a signal that activates dopamine pathways, reinforces habitual behaviors, and conditions the palate. Artificial sweeteners used in these beverages are often hundreds of times sweeter than natural sugar, creating an intensity that far exceeds what the human body evolved to experience. Over time, this overstimulation of sweetness can rewire the brain's reward system, making naturally sweet or less processed foods seem bland and unsatisfying by comparison. This shift in preference can drive a cycle of craving, overconsumption, and poor glycemic control. At the center of this cycle is the nucleus accumbens, a region of the brain deeply involved in reward, pleasure, and motivation. This part of the brain is activated not only by sugar, but also by the artificial compounds used in diet sodas. When stimulated repeatedly by intense sweeteners, the receptors in this area may undergo neuroplastic changes. The result is a heightened expectation for sweetness and a damp response to natural foods. Fruits, vegetables, whole grains, foods that support stable blood sugar, may no longer provide the same satisfaction. Instead, the brain begins to seek out foods that deliver a comparable dopamine release, often leading to increased consumption of refined carbohydrates and processed snacks that promote postprandial glucose spikes. This mechanism is not hypothetical. Neuroimaging studies have shown that artificial sweeteners can activate the same brain areas as sugar, but the activation patterns differ in key ways. While sugar tends to produce a complete reward loop, taste, caloric satisfaction, hormonal feedback, artificial sweeteners only partially satisfy this loop. The brain senses sweetness but receives no energy in return. Over time, this mismatch may reduce satiety, increase food-seeking behavior, and lead to compensatory eating. The brain keeps signaling food because the expected calories never arrive. This disconnect has been observed in functional MRI scans showing reduced hypothalamic activity following diet soda consumption compared to sugar-sweetened beverages, indicating impaired energy regulation signaling. Another consequence of this repeated exposure to intense sweetness is what researchers call hedonic adaptation. Just as someone exposed to loud noise over time becomes less sensitive to volume, someone exposed to hyper-sweetened beverages becomes less sensitive to subtle flavors and natural sweetness. This desensitization can be problematic when it comes to dietary quality. People may find themselves rejecting health, promoting foods not because they are unhealthy, but because they no longer satisfy the recalibrated palate. Over time, this preference for more intensely sweetened products may result in a diet dominated by foods that contribute to glycemic instability, weight gain, and insulin resistance. This alteration in taste preference also intersects with behavioral psychology. Diet sodas are often consumed under the belief that they offer a free pass, a sweet reward with no metabolic cost, but this perception can backfire. Individuals may pair diet soda with high-calorie meals or use it to justify indulgence elsewhere. The brain, driven by the incomplete satisfaction of the sweetener, may push for a second helping or a sugary dessert that it might not have craved otherwise. These subtle behavioral changes, magnified over weeks, months, and years, can result in measurable changes in metabolic health and blood sugar regulation. There is also evidence that frequent consumption of artificial sweeteners may alter signaling from the gut to the brain. The gut contains specialized cells called enteroendocrine cells that release hormones in response to food, such as GLP-1 and PY. Not only help regulate insulin secretion but also communicate fullness and satiety to the brain. Artificial sweeteners can bind to receptors on these gut cells and may disrupt the normal hormonal feedback loop. If satiety signals are weakened, the brain may fail to register fullness after a meal, leading to increased caloric intake and more frequent snacking. This impaired hormonal signaling may further reinforce cravings for sweet foods, drive overconsumption, and ultimately lead to glucose dysregulation. When taste preferences shift toward highly sweetened products, and when those products provide incomplete feedback to the brain and gut, the entire network that regulates energy balance becomes compromised. The brain no longer trusts sweetness as a reliable predictor of energy. The gut no longer signals satiety effectively. And the result is a confused metabolic system more prone to blood sugar fluctuations and poor insulin control. Appetite regulation is a delicate system controlled by hormonal signals that travel between the gut, pancreas, liver, fat cells, and brain. This system relies on finely tuned feedback loops that monitor nutrient intake, energy storage, and satiety. When artificial sweeteners from diet sodas are introduced in this environment, they may disrupt key hormones that regulate hunger and fullness, leading to increased appetite, erratic eating patterns, and ultimately metabolic imbalance. These disruptions can be subtle at first, but over time they may contribute to weight gain, glucose dysregulation, and increased risk for insulin resistance. Among the most important ones affected by sweeteners are G1 glucagon, like peptide 1, leptin, ghrelin, and insulin. GLP-1 is secreted by cells in the intestines in response to food intake. It slows gastric and promotes satiety and enhances insulin secretion in a glucose-dependent manner. Some artificial sweeteners have been shown to interfere with GLP-1 signaling, either by overstimulating its release without corresponding calories or by downregulating its receptors over time. This can blunt the feeling of fullness after meals and impair the body's ability to handle post-meal glucose efficiently. When GLP-1 levels are disrupted, insulin secretion may also be less responsive to actual nutrient intake, creating confusion in the body's glycemic control systems. Leptin, a hormone secreted by adipose tissue, communicates with the hypothalamus to signal long-term energy storage and suppress appetite. Chronic consumption of artificial sweeteners may disrupt leptin sensitivity, especially when paired with other metabolic stressors such as poor sleep, high stress, or ultra-processed diets. Leptin resistance, similar to insulin resistance, results in a state where the brain no longer accurately perceives the energy reserves. This can drive persistent hunger, even in the context of adequate or excessive calorie intake, pushing individuals toward overeating and carbohydrate-heavy choices that destabilize blood sugar. At the same time, ghrelin, often called the hunger hormone, may also be impacted. Ghrelin levels rise before meals to stimulate appetite and decrease afterward to signal fullness. Some studies have shown that artificial sweeteners may not suppress to the same extent as natural sugar, meaning that the brain continues to perceive hunger even after consumption of a sweet-tasting beverage. This effect is particularly concerning because it can lead to increased meal frequency or larger portion sizes, both of which contribute to elevated insulin levels and impaired glucose tolerance over time. Another critical factor is the timing and intensity of insulin secretion. Artificial sweeteners can stimulate release through a mechanism known as the cephalic phase insulin response, where the anticipation of calories based on sweet taste prompts the pancreas to secrete insulin before nutrients even arrive in the bloodstream. While this response is adaptive in moderation, frequent activation without caloric follow-through may lead to hyperinsulinemia, a condition where insulin remains chronically elevated. Elevated insulin promotes fat storage, reduces lipolysis, and can cause blood glucose to drop below normal, creating a rebound hunger signal that encourages additional food intake. This pattern reinforces a vicious cycle of eating, insulin release, and hunger that can destabilize blood sugar over time. Overconsumption driven by disrupted hunger signals is often compounded by the behavioral psychology surrounding diet soda. Many people who consume diet beverages believe they are making a healthy choice and may compensate by indulging elsewhere. This phenomenon, known as the licensing effect, has been observed in behavioral studies where individuals who choose diet drinks are more likely to consume high-calorie snacks or meals afterward. This combination of physiological hunger and psychological justification can lead to a higher overall caloric intake than if no diet soda had been consumed at all. It's also important to consider that artificial sweeteners affect different people in different ways. Staying away from processed foods, individuals with higher baseline resistance may be more sensitive to the appetite-disrupting effects of sweeteners. Others may have variations in their gut microbiota that modulate hormonal responses differently. Some people may feel hungrier after drinking a diet soda, while others may not notice any change. But across large populations, the data suggest a pattern of increased appetite and disrupted metabolic signaling among regular consumers of artificially sweetened beverages. The long-term result of these hormonal and behavioral disruptions is often a gradual increase in caloric intake, weight gain, and worsening glucose control. Even though diet sodas may not directly elevate blood sugar in the short term, the secondary effects through increased appetite, altered satiety, hormonal miscommunication, and insulin overcompensation create an environment where blood sugar becomes harder to manage and insulin sensitivity gradually declines